Hello everyone, welcome to Kanitama's channel. In this video series, we will be discussing CBSE Class 12 Maths. In this subject, we are having 13 chapters in total, 6 chapters in Volume 1 and 7 chapters in Volume 2. So in this video, we will be discussing the Chapter 1, Relations and Functions. So in Class 11, you have discussed in detail about set and Cartesian product and you have the basic knowledge on relations and functions. So in class 12, we are going to discuss about the types of relations and functions. Also, we will be discussing composition of functions and invertible functions. Before getting into the idea of types of relations and functions, we will have a quick revision on the ideas of set and Cartesian product. A set is defined to be a well-defined collection of objects. Here, the term well-defined is very important because if the elements in the collection are not well defined, then we cannot consider it to be a set. Example for set are set of even numbers, set of all students in class 12 in a particular school, and set of numbers which are less than 500. So all these are all examples for set. Here the elements inside the collection are well defined. There are examples for the collection of objects which are not set. For example, collection of beautiful flowers in the garden. So here the term beautiful flowers is not well defined because the term beautiful will differ from person to person. One may think jasmine to be the beautiful flower and another person can think rose to be a beautiful flower. So we cannot come to a conclusion whether to include that. So it will vary from person to person. Therefore, the collection of beautiful flowers in the garden is not defined to be a set. In class 11, you have studied the different types of set and the operations that could be performed between the sets. And now let us move on to the idea of Cartesian product. Cartesian product between two non-empty sets, say A and B, is denoted using the notation A cross B. This Cartesian product A cross B is defined to be the collection of all possible ordered pairs A comma B such that A belongs to the set capital A and B belongs to the set capital B. And the ordered pairs should be in such a way that the first element should always represent the first set and the second element should represent the second set. So here each and every element in A will be mapped to each and every element in B. So here we will be having all possible combinations of the elements of A and the elements of B. So without any condition, each element in A will be mapped to each and every element in the set B. The next one is relation. Relation is said to be a subset of Cartesian product because only the ordered pairs which satisfies the condition given will be included in relation. So relation is considered to be a subset of A cross B. For example, if I consider two non-empty sets A equal to 1, 2, 3, etc. up to 10 and B equal to 3, minus 5, 2, minus 8, and now if I define the relation R such that it consists of ordered pairs A comma B such that A is related to B with the condition that A is less than or equal to B. So, if the element of A is less than or equal to element of B, then the ordered pairs A comma B will be included in the set R. So now in this example, we will be having the ordered pairs 1 comma 3, 2, 3, 3, 3, 2, 2 and 1, 2. So here we can observe that the first elements in each pair will be less than or equal to the second element in the ordered pair. Therefore, only these elements will be included in the relation R, whereas in A cross B, each and every element in A will be mapped to the elements in B. Thus, the relation is said to be a subset of A cross B. The set of all first elements in the ordered pairs in this collection R will be considered to be the domain of this relation R, and the set of all second elements in this collection of ordered pairs will be considered to be the range of this relation R. So in general, not every element in the set A will be mapped to the elements in B. Next, moving on to the idea of functions. Function is a subset of relation because here we impose further conditions on relations such that each and every element in the set A will be mapped to elements in B, and each and every element should have a unique image in the codomain B. So, a relation with these two conditions are said to be functions. In general, we write function from two non-empty sets A and B to B such that f is a function from A to B, where f of x equal to y for every x belongs to the set A. So it is to be noted that each and every element in the domain should be mapped to elements in the set B, where A is the domain of the function and B is the codomain of the function, and range of the function is defined to be set of all elements in the codomain such that there exists one element in the domain so that element x will be mapped to y. In this chapter, we will be discussing about the types of functions and special ideas of functions known as composition and invertible functions. So let's get started. Section 1.2, types of relations. When you consider a non-empty set A relation is a subset of A cross A. So, an empty set and A cross A are two basic relations for every non-empty set A. So, here they have given an example. If you consider a set A which consists of elements 1, 2, 3, 4, and here they have defined a relation R such that it consists of the collection of ordered pairs A comma B such that A minus B equal to 10. So only the elements satisfying this condition A minus B equal to 0 will be included in the relation. But the elements in the set A are 1, 2, 3, 4. If you subtract them, you will not get the answer to be 10. So no elements will be there in the set R. Therefore, this set R is an empty set. One more relation they have defined, R dash equal to set of all ordered pairs A comma B such that absolute value of A minus B is greater than or equal to 0. So if you find the difference between the elements of A and their absolute value should be greater than or equal to 0. So all the elements in the set A will satisfy this condition. Therefore, this set R dash will consist of all ordered pairs which are in the Cartesian product A cross A. Therefore, this set R dash is equal to the Cartesian product A cross A. So from these two examples, we can define the following two types of relations known as empty relation and an universal relation. So if a relation has no element of A, then we call that relation to be an empty relation. So R equal to empty, again it is considered to be a subset of A cross A. A relation in a set A is called empty relation if it consists of no elements of A and R is defined to be empty, but still it remains to be the subset of A cross A. A relation R in a set A is called universal relation if each and every element of A is related to every element of the set A itself. So here R is equal to the Cartesian product A cross A. These two relations, empty relation and universal relation, are known to be trivial relations. Example 1. Let A be the set of all students of a boys' school. Show that the relation R in A given by R equal to set of all ordered pairs A comma B such that A is sister of B is the empty relation and R dash equal to set of all ordered pairs A comma B such that the difference between heights of A and B is less than 3 meters is the universal relation. So here they have given the set A to be collection of all students in a boys' school. So each and every element in this set will be a boy. Now they have defined two relations. One is R equal to set of all ordered pairs A comma B such that A is sister of B. So the elements which satisfies this condition will be included in this relation R. One more relation R dash such that the elements which satisfies the condition difference between heights of A and B is less than 3 meters will be included in this set. Now we have to prove that these two relations are empty relation and universal relation respectively. One thing we can observe that the set A consists of only boys, therefore the relation is sister of will never get satisfied between the elements A and B from the set A. Therefore this set R will have no elements. Thus the relation R is considered to be empty relation. When we consider the relation, the difference between heights of A and B is less than 3 meters. It is obvious that the difference between the heights of two boys will be definitely less than 3 meters. Therefore, all boys in the school will be included in the set R dash. Therefore, all possible ordered pairs A comma B will be included in this set R dash. Therefore, R dash will be equal to A cross A. Thus, R dash is a universal relation. And relation can be defined in two different forms. One is roster form and another one is set builder form. We can also express the relation such that the elements or the ordered pairs A comma B will be included in the set R only if A is related to B. And the next idea what we are going to discuss is equivalence relation. It is a very important topic. Before getting into that idea, we should know the following terms: reflexive, symmetric and transitive. A relation R in a set A is called reflexive if each and every element in a set A is related to itself. That is, the ordered pair A comma A belongs to the relation R for every element A in capital A. If you consider two elements in the set A, namely A1 and A2, then if A1 is related to A2, this should imply A2 is related to A1. That is, if the ordered pair A1, A2 belongs to R, then A2, A1 should also belongs to R. If this condition got satisfied, then we call the relation R to be symmetric. If you consider three elements, say A1, A2, A3 in the non-empty set A, and if A1 is related to A2 and A2 is related to A3, then we should get A1 is related to A3. If this condition got satisfied, then we call this relation R to be transitive. So, if any relation satisfies all these three conditions, then we call that relation to be equivalence relation. So, example 2, let T be the set of all triangles in a plane with R, a relation in T given by R equal to set of all ordered pairs T1, T2 such that T1 is congruent to T2. Show that R is an equivalence relation. So here they have considered a non-empty set T which consists of all triangles in a plane with a relation R such that if you take any two triangles, they should be congruent. Only such elements will be considered in the relation R. Now we have to prove R is an equivalence relation, which means we have to prove R is reflexive, symmetric and transitive. Now, when can you say two triangles are congruent? If all the sides and angles are same, then we call the two triangles to be congruent. In our case, if you take a triangle, it will be congruent to itself because the sides and angles will be equal to itself. Therefore, R is reflexive. Now, if you consider two triangles T1 and T2 such that T1 is congruent to T2, now we have to find whether T2 is congruent to T1. Since T1 is congruent to T2, we know that the sides and the angles of both the triangles are equal. Therefore, we can say T2 is congruent to T1. Therefore, the ordered pair T2, T1 belongs to the relation R. Thus, R is a symmetric. Now, if you take three triangles T1, T2, T3 such that T1 is congruent to T2 and T2 is congruent to T3, now we have to check whether T1 is congruent to T3. Since T1 is congruent to T2, sides and angles between T1 and T2 will be equal. Also, T2 and T3 are congruent. So, this implies the sides between the triangles T1 and T2 and the angles are all equal. So, we can say the sides between T1 and T3 will be equal, similarly the angles. Therefore, we can say T1 and T3 are congruent. Therefore, the relation R is transitive. Since the three properties got satisfied, we can say the relation R that T1 is congruent to T2. Equivalence relation. Example 3. Let L be the set of all lines in a plane and R be the relation in L defined as R equal to set of all ordered pairs L1, L2 such that L1 is perpendicular to L2. Show that R is symmetric but neither reflexive nor transitive. So here they have considered the non-empty set L which consists of all lines in the plane and they have defined the relation R on the set L such that if L1 is perpendicular to L2, then the ordered pair L1, L2 will be included in this relation. Now we have to prove that this relation R is symmetric but it is not reflexive and transitive. First, let us take the property reflexive. When can you say a relation to be reflexive? If every element is related to itself, then we call it as reflexive. So if you take any one element L1, we have to check whether it is perpendicular to itself. But this is not true. Therefore, the relation R is not reflexive. Moving on to the second property, symmetric. If you take two lines L1 and L2 such that L1 is related to L2, that is L1 is perpendicular to L2. Now we have to check L2 is perpendicular to L1. So if I take this line L1 and if this line L1 is perpendicular to L2, then we can also say L2 is perpendicular to L1. So what we could conclude is L2 is perpendicular to L1. Therefore, the relation R is symmetric. Moving on to the third property, transitive. If you take three lines L1, L2 and L3 such that L1 is perpendicular to L2 and L2 is perpendicular to L3, whether we can say L1 is perpendicular to L3. Looking at the figure 1.1, from this we can say L1 is perpendicular to L2 and L2 is perpendicular to L3. But L1 and L3 are not perpendicular, they are parallel to each other. Therefore, the ordered pair L1, L3 is not included in the relation R. Therefore, R is not transitive. So, thus we have verified R is symmetric but not reflexive and transitive. Example 4. Show that the relation R in the set 1, 2, 3 given by R equal to set of all ordered pairs 1, 1, 2, 2, 3, 3, 1, 2, 2, 3 is reflexive but neither symmetric nor transitive. So here they have given the non-empty set which consists of the elements 1, 2, 3 and they have given the elements in the relation. So they have given it in the roster form. So from the set R given to us, we can observe that the elements of the set A, 1, 2, 3 are related to itself, such that the ordered pairs 1, 1, 2, 2 and 3, 3 are there in the set R. Therefore, the relation R is reflexive. Since the ordered pair 1, 2 is there, but we don't have 2, 1. Therefore, this relation R is not symmetric. Moving on to the third property, transitive. Here we have the ordered pairs 1, 2 and 2, 3. Therefore, 1 is related to 2 and 2 is related to 3. But we don't have the ordered pair 1, 3. Therefore, 1 is not related to 3. Thus, we have proved that R is not transitive. Example 5. Show that the relation R in the set Z of integers given by R equal to set of all ordered pairs A, B such that 2 divides A minus B is an equivalence relation. So the set what we have to consider is set of all integers. The relation they have given is such that if A minus B is divisible by 2, then it will be included in the set R. Now we have to prove that R is an equivalence relation. That is, we have to prove it is reflexive, symmetric and transitive. Number 1, reflexive. So we have to prove that A is related to itself, which means A minus A is divisible by 2. When you take any integer, if you subtract it from itself, then the answer will be 0. In general, 0 is divisible by any non-zero number. So 2 will divide 0. Thus, we have proved that A is related to itself. So we can say R is reflexive. Moving on to the second property, symmetric. If you take two elements A and B in the set Z such that A minus B is divisible by 2. Now we have to prove that B is related to A. That is, B minus A is also divisible by 2. It is given that A is related to B such that A minus B is divisible by 2. It is obvious that 2 will also divide B minus A. Therefore, we can say that B is related to A. So, the relation R is symmetric. Moving on to the third property, transitive. If you take the elements A, B, C from the set of integers such that A is related to B and B is related to C, now we have to prove A is related to C. Since A and B are related, A minus B is divisible by 2 and B minus C is also divisible by 2. Now we have to prove A is related to C, that is A minus C is divisible by 2. So if you add and subtract B, you will get A minus B plus B minus C. We know that A minus B is divisible by 2 and B minus C is divisible by 2. Any number which is divisible by 2 should be an even number. Therefore, we can say A minus B is an even number and B minus C is an even number. If you add two even numbers, you will be resulted with an even number. So, this must be an even number. So, every even number is divisible by 2. Therefore, A minus C is also divisible by 2. So, thus we have verified A is related to C. So, the relation R is transitive. We have proved that the relation R is an equivalence relation. From the above example, we can observe that 0 is related to all even integers, because if you take one element say A to be 0 and another element to be an even integer, and if we find the difference between them, it will be equal to that even integer which is divisible by 2. Therefore, all even integers are related to 0. In case if you take one element to be 0 and another element to be odd integer, and their difference will be equal to that odd integer which is not divisible by 2. So what we could conclude is no odd integer is related to 0. Similarly, if you take one element to be 1 and another element to be an even integer, their difference will be an odd integer which is not divisible by 2. Therefore, set of even integers will not be related to 1. If you take one element to be 1 and the other element to be odd integer, then their difference will be equal to an even integer which is divisible by 2. Therefore, all odd integers are related to 1. Therefore, the set E of all even integers and the set O of all odd integers are subsets of set of integers with the following conditions: that all elements of the set of even integers are related to itself. Similarly, all elements of odd integers are related to itself. And no elements from the set E is related to the elements in the set O, and vice versa. And E and O are disjoint, such that their union will be equal to set of integers. So from this, what we could conclude is the set E is called an equivalence class containing 0 and is denoted by this notation. Similarly, O is the equivalence class containing 1 and is denoted by this notation. And it is to be noted that these two equivalence classes are not equal, and the equivalence class 0 is equal to the equivalence class 2r, where r is an integer, and the equivalence class 1 equal to equivalence class 2r plus 1, again r is an integer. It is to be noted that if you consider an arbitrary equivalence relation R in an arbitrary set X, then this relation R divides the set X into mutually disjoint subsets AI called partitions or subdivisions of X, satisfying the following conditions. All elements of A are related to each other for all I. No element of AI is related to any element of AJ where I and J are not equal, and the union of AJ equal to the whole set X, and the intersection between AI and AJ will be empty set. So these subsets AI are called equivalence classes. Here they have given an example in which they have considered a subdivision of the set of integers given by three mutually disjoint subsets A1, A2 and A3 whose union is Z, with A1 equal to set of all x belongs to Z such that x is a multiple of 3. So it consists of the elements -6, -3, 0, 3, 6, etc. And A2 equal to set of all x belongs to Z such that x minus 1 is a multiple of 3. It consists of the elements -5, -2, 1, 4, 7, etc. And A3 consists of set of all x belongs to Z such that x minus 2 is a multiple of 3, which is equal to -4, -1, 2, 5, 8, etc. We can observe that if you take the union of A1, A2, A3, then it will be equal to the set of integers, and if you take any two sets, they will be disjoint. They have also defined a relation R in Z, which is given by set of all ordered pairs A, B, such that A minus B is divisible by 3. It is to be noted that this relation R is an equivalence relation. Let us prove that. Number 1, reflexive. If you take any element from the set A2, say A, such that A minus 1 is a multiple of 3, therefore it is divisible by 3. Now we have to verify whether A is related to itself. That is, A minus A is divisible by 3. Since A minus A equal to 0, which is divisible by 3, we can say A is related to A. Therefore, R is reflexive. Second one, symmetric. If you take two elements from the set, say A, such that two elements are multiples of 3. Therefore, A is divisible by 3 and B is also divisible by 3. Now, we have to verify that A related to B implies B related to A. Since A is related to B, A minus B is divisible by 3. This implies B minus A is also divisible by 3. Thus, we have proved B is related to A. Therefore, the relation R is symmetric. Moving on to the third one, transitive. If you take 3 elements from the set, say A3, such that A related to B and B related to A should implies A related to C. Now I need to prove A is related to C. That is, A minus C is divisible by 3. A minus C can be written as A minus B plus B minus C. Since A minus B is divisible by 3, it is a multiple of 3. So it can be written as 3z1, where z1 is an integer. Similarly, I can write B minus C as 3z2. If I take 3 outside, since z1 and z2 are integers, their addition is also an integer. Thus, I have written A minus C as a multiple of 3. From this, what I can conclude is A minus 3 is divisible by 3. So, the relation R is transitive. Thus, we have verified the relation R is an equivalence relation. It is to be noted that the set A1 coincides with the set of all integers in the set Z which are related to 0, and the set A2 coincides with the set of all integers which are related to 1, and A3 coincides with the set of all integers in Z which are related to 2. Thus, we can write is A1 as the equivalence class of 0, A2 is equivalence class of 1, and A3 as equivalence class of 2. We can write A1 as equivalence class of 3R, A2 as equivalence class of 3R plus 1, and A3 as the equivalence class of 3R plus 2, where R is an integer. Example 6. Let R be the relation defined in the set A equal to 1, 2, 3, 4, 5, 6, 7 by R equal to set of ordered pairs A, B such that both A and B are either odd or even. So, only the elements which satisfies the condition that both A and B should be either odd or even number. Then only they will be said to be related. Show that R is an equivalence relation. Further, show that all the elements of the subset 1, 3, 5, 7 are related to each other, and all the elements of the subset 2, 4, 6 are related to each other, but no element of the set 1, 3, 5, 7 is related to any element of the subset 2, 4, 6. So, the non-empty set given to us is A, which consists of the integers from 1 to 7, and they have given a relation. Now we have to prove this relation is an equivalence relation. So number 1, reflexive. If you consider any element A in the set A, it will be either even or odd. So what we could conclude is both A and A must be either odd number or even number. Therefore, the ordered pair A, A will be included in the set R. Thus, the relation is reflexive. Second one, symmetric. If you take two elements A and B from the set A such that A is related to B, we know that both A and B must be either odd or even number. So what we could conclude is B is related to A. Therefore, the relation R is symmetric. Third one, transitive. If you take three elements from the set A such that A is related to B and B is related to C, then we have to prove A is related to C. So this implies A, B, C, all the three numbers should be either even or odd. So from this what we could conclude is A is related to C. Therefore, the relation R is transitive. Thus, we have proved R is an equivalence relation. Also, we need to verify that the elements of the subset 1, 3, 5, 7 are related to each other. Since this subset consists of only odd numbers, definitely they will be related to each other. If you consider the subset 2, 4, 6, all the elements are even numbers. So, all the elements are related to each other. And it should be noted that if you take an element from the subset 1, 3, 5, 7 and an element from the subset 2, 4, 6, they are not related because the first subset consists of odd numbers whereas the second subset consists of even numbers. So they are not related as per the relation defined in this problem. We'll discuss the exercise 1.1 in the next video. If you have any doubt, comment in the comment section. If you like the video, click the like button and share the video to your friends. And please subscribe to the channel. Thank you.